Hey. So I know that this is the last presentation of today and people are waiting for the after party, so we'll try to keep this short. But yeah, I'm excited about this presentation because we, like at Rippling, we do an HRIS system which is very complex, and Temporal is really nice use.
Yep. Okay, slides are up.
You can see that.
Okay. We are here from Rippling to talk about how we are using Temporal. So brief agenda is the workflows of Rippling. As a platform team, what are our challenges and what are our objectives as a platform team. So we've got some good reception, and we also have feedback from our developers. And we also want to talk about what are we going to do in the future. So workflows at Rippling. So before we talk about workflows at Rippling, we want to give an intro on what is Rippling. Rippling is a HR startup that lets you manage your employees, payroll, benefits, expenses, devices, and many other things, all things at one place. So if there are multiple domains and all these domains get tied at one place. So this is very obvious in our website, where we talk about workflow automations. And workflow automations are a very integral part, where you might want to do something like an automated notification at the end of 90th day of an employee, set up an automatic meeting invite for every employee. So most of the administrative work is taken away, and people can focus more on things that they need to do. So this is what we offer to all the HR admins. And these workflows follow a simple event, condition, action pattern. So you define an event, condition, and what is a corresponding action to that workflow. So these are fully customizable, and as an HR admin on Rippling's platform, you just define these conditions and actions. So behind the scenes, we use Temporal as one of the execution engine, and these user workflows translate into internal workflows.
Yeah, so the other type of workflows that you can see on the slide is internal workflows. So those are kind of more complicated than a simple event condition action, because they drive the main decisions that our system does internally, which means like you can probably think of like HR is very different at different companies at different locations, like different countries, and all of those decisions have to be encoded somewhere. So that's kind of like what I mean by internal workflows. Those workflows are usually product defined, and we can fully utilize not just a Temporal as execution engine, but also as a DSL, because we want like a nice way to read through the workflow, not just execute it through Temporal. But first, before we go like into actual Temporal stuff, let's start with how we were dealing with this sort of workflows at Rippling before like anything, like before we even mentioned workflows as a concept. So Rippling started, as many startups, as a create, read, update, delete sort of application, where there was a Mongo at the base, and like every action was just translated into some sort of write and read to the database, and that was pretty much it. And at that point, when you want to react to some sort of changes and implement some sort of cross-cutting concerns, the only option you really have is to react on ORM events. So you just capture that, for example, employee status has changed from onboarding to active, and then you know that probably onboarding has finished, and then at that moment you execute some action And you process that action and, like, I don't know, send an email or schedule some sort of interview or something like that. And sometimes you, while doing that processing, you modify another entity which triggers another event, and then you have like this cascading chain of events, which technically from afar looks kind of like a workflow, just like in a different projection. Like you just have a chain of actions that happened because the person finished onboarding. And however, those sort of kind of like quote unquote workflows are very difficult to maintain because they're not really even workflow. They're kind of like accidental workflows. And obviously difficult to debug, not reliable, happens only in memory, therefore like not durable in any way. And yeah, it was just like really terrible thing to deal with. Then, kind of independently from that problem, a separate team in Rippling invented this subsystem called ETA, which is just like a play of words on estimated time of arrival. The goal of the system was to provide a kind of like a platform similar to AWS Lambda, where you can just throw a task at it and some worker somewhere will execute that task and give you back the result. And that was completely independent from events, but the interesting part about it was to provide this sort of execution in the cluster in a durable way. It had to serialize and persist all the inputs and outputs from each of those functions. And given that all the inputs and outputs are serialized, you could already imagine that it would be able to do retries, it would be able to do like durable stuff, it could postpone the execution in the future if there is not enough workers. Like essentially it's much better system already than the event processing that I mentioned in the previous slide. And because of that, and because of very good DSL that allows to use that ETA directly from Python code, very transparently, just take this function and just execute it in the cluster, people started migrating their workflows and actually like building new workflows on this ETA, even though ETA was not meant for that. Like it was meant for a completely different task, and it looks like even from the code structure, it's still like a chain of function calls that just like call each other in a random pattern, and again, it's very disorganized, very difficult to, like there is no concept of workflow, it's just like a chain of functions that happen asynchronously throughout the cluster, like through those workers. So again, like even though it was much better because everything is serializable and durable, it was still a mess and difficult to debug, difficult to reason about. So with that in mind, platform team decided to add a new objective to the list and to provide a nice way for teams to define their workflows, to manage their workflows, to execute their workflows. Essentially make workflow a first-class citizen in Rippling like platform ecosystem. So for that we defined like such objectives, like conceptually, having a concept of workflow as a first-class entity itself is super important because that allows, for example, even communicating across teams is easier. You are not dealing with things like my function calls that function, or like when this event happens, you do that stuff. You actually reason with workflows. You say that like when the person is onboarded, let's do onboarding workflow, which has 5 steps in it. So suddenly communication becomes easier. Traceability, conceptualization, debugging. Like all of those are very important conceptual objectives. Functionally, obviously, persisted workflow state for durability, retries, partial retries, timeouts, throttling, prioritization, like all of those standard things. And organizationally, a super important thing that we put as a goal was because the platform team responsible for asynchronous event processing was very tiny at the time, and we thought that it makes sense for teams to just self-service this stuff. So we would like to have minimal impact, like only like if we really need to help with something, but like mostly provide tooling to the teams, and then every team should be able to just do their own thing, create workflows, create activities, like whatever they need to make that work. And because Rippling is trying to also adopt a microservice architecture, we would also need that to happen across multiple languages. So with that in mind, you probably saw like from previous slides that temporal pretty much checks all the boxes, like that's basically the definition of temporal. But still there were some challenges and solutions we had to solve, so I'll quickly run through those as well. First of all, Python. I don't think Python SDK, like if it's like officially released, it was in beta version when we started dealing with it. But one problem with Python is how coroutines in Python are very there is no strict separation between asynchronous code and synchronous code. You can call synchronous code from asynchronous one, and you wouldn't know that something somewhere is blocking something else, and your entire event loop is now blocked by that by some code that's calling and waiting on the database. So that's not a problem for workflows per se, because workflows don't need to be, like, they cannot be blocking. But for activities, it becomes a problem, especially in our case when we had a monolith in place. Because in monolith, you have a lot of legacy code. There is some function somewhere that says, is employee active? And it sounds like a Boolean check, but in reality, it does 5 calls to the database under the hood, like 3 levels deeper. And also, like in reverse, the same problem also applies, because when someone modifies a method, they need to know the context of the execution of that method. And now if that method is executed from a coroutine, you need to know that you're not allowed to block from there. So even though we started by allowing team and actually encouraging them to use asynchronous code, because we were trying to like, hey, let's adopt the newest, bestest practices in Python, we quickly realized that this requires a lot of hand-holding, and we essentially just ended by disallowing using any asynchronous code for activities, like, I mean, coroutines specifically in Python. Then the next challenge, which is quite obvious one, was provide some way for easily migrating from ETA and from events to this new like temporal-based workflow system. So first of all, we identified this interesting pattern that in that ETA world, we always had, like very frequently there was this pattern of one ETA being kind of like an orchestrator, like pretty much a workflow, or at least like almost a fully orchestrator. And then a bunch of other ones that were doing actual work. So this naturally translates to workflows and activities in temporal, but how do we encourage that and provide like some partial, like way to partially migrate this, like instead of rewriting like everything from beginning to the end. So we went with this approach. We provided an interesting way to have a temporal to ETA bridge. Essentially, from a temporal workflow, you are able to run any ETA that currently exists in our monolith, and that ETA will be wrapped in, like it will present itself as an activity. So workflow can deal with it, workflow can manage its state, life cycle, everything. Like it appears as an activity from workflow perspective, but from the code perspective, it's still an ETA, and it's being run in ETA cluster, in ETA cluster of workers. So still all the like previous guarantees from ETA world still apply, so nothing is being broken. And this allows a nice top-down migration, because now people can start migrating already the existing code by migrating the highest, like the most important layer, the one that orchestrates work, migrating it to temporal. And another important thing is, because ETA was not built for this sort of asynchronous work, it does not support any sort of signaling. And that means that when the high-level orchestrator waits for the children to finish the work, it's essentially blocking the entire Python application. Like it just sits there doing nothing, taking resources and like waiting for half an hour for all that work to complete. With temporal now suddenly, just by doing this step alone, we allow to release those resources. Because when the ETA function and the underlying one completes, we can now only then restore the context and continue execution of the workflow. And obviously, we had to provide various other primitives that we had already built in the system, like serialization of various primitives that we were sending to ETA and back, like various like complex ID objects, and some primitives like a simpler way. Like a very common pattern was a scatter-gather mechanism, and we also wanted to move that to temporal, so we also provided like simple helper functions to implement it easily. When we did the first iteration of temporal, we had this team, Hindsight, which was responsible for processing auditing information. And they were essentially reacting to various events in the system and doing like an audit-related post-processing. And they complained to us that their work is being postponed, that essentially there is a delay of up to 5 minutes or sometimes more, and they have very strict SLAs on their work, and because of those SLAs they cannot really work correctly. And we started investigating this, and we quickly realized the problem. Like in our original implementation, we went with the approach again from the ETA world, kind of like translated like the most simpler way. And the approach from ETA was to just provide one big shared pool of workers, and then somehow figure out prioritization after you read from the queue. But this does not work well, like in general, I would say. Like that's a bad idea, because first of all, you need a really good scheduler. You need to have some sort of really good algorithm to figure out which objects to pick from the queue, like which tasks to pick from the queue in which order, and also figure out like which ones can you run in parallel in each specific worker, so that there is enough resources. Like what if one takes 1 gigabyte of memory and another task takes like 1 megabyte of memory? Like can you really parallelize them together? Like you can run 100 of those, but only one of like the other. So we quickly realized that we cannot really work with shared worker pool because we just don't have resources to have that like super fancy and super smart scheduler in place. Instead, we decided let's do the opposite approach. Everyone creates a worker pool. Like you need a task queue, you create worker pool, you create everything. For this, obviously, we need to provide good tooling, which we built already. So we have a shared Helm chart, shared Terraform module, and it's really easy. You just create a Terraform resource, and you suddenly have a pool of workers reading from specific queue. Everything is automatically provisioned, which, to be fair, Monolith makes easier. But yeah, that's essentially how it works right now. And with private worker pools in place, suddenly all those issues become non-issues. Like for prioritization, like you need a high priority queue, just create a new pool of workers, like make a lot of them there, like if you need them super low latency. If you need low priority, create one worker that downscales to 0 automatically, like again, based on the queue size. Like noisy neighbors, also not a problem. You don't have neighbors by definition, like you just have your own private worker pool. Debugging issues, misconfiguration issues, like all of that is up, like completely on you. Like you are responsible for what's happening in your worker pool. And finally, another minor thing that we had to deal with was scheduling workflows in time. Like originally before Temporal 1.17, there was no good way to schedule workflows except by like during the creation of the workflow itself. So like when creating the workflow, you provide a cron definition and then that workflow is created. But now when you try to do that on scale, when you have like hundreds of workers running, and now we need to figure out like, so when exactly do I create that workflow at this point? Like I want to create it in the same code base, but when it's deployed, I now suddenly have 100 workers coming up at the same time, so all of them will try to create the same workflow. So now you need to deal with exceptions, and you need to do something like, hey, idempotency exception, this workflow already exists, let's assume that it's already scheduled with the right timing. And if you need to change timing, then you need to do manual work and remove it from the like registry and create a new. Hopefully, in Temporal 1.17, there was added a new temporal schedule API, which we haven't had time to work with yet, sadly, but we already have plans for it. And the idea is to, again, provide just a separate Terraform provider that would allow people to, again, in Terraform, just define a schedule for their workflow, which would mean that if you have a schedule in place, you just put it in Terraform, and when it's being provisioned, you have it registered in Terraform, in Temporal cloud. And we generally got really good reception, and interestingly enough, a lot of teams are coming to us and just asking like, hey, we have this problem, like, can we use Temporal? And a lot of times it's not really a good case, but still it's kind of like a good signal, I would say, that people are really interested, really looking forward to adopting this new technology, and we just need to guide them in the right way, like how to correctly use it. And there was still some feedback from teams that were not fully satisfied, or like just had some issues that were unexpected. So let's also quickly go through that feedback.
So one of the feedback that we've been getting from newer adopters of Temporal at Tripling is leaky abstractions. So what do I mean by leaky abstractions is they jump right to define their workflow, their activities, and they expect it to work. Sometimes they forget about side effect management. So most of the time we are running in a monolith on Python. They are kind of bringing in a lot of stuff which comes as internal code. And they just start defining, and they don't realize it as a blocking code. 5 downs or 5, 6 levels down, it is waiting for I/O or is making a database call. So they forget about the semantics of designing a workflow. Sometimes the workflow code looks very familiar to them, or they think it is a code. I can add a new argument to it. They forget about the serialization of the workflow. So, workflow versioning also has to be implicitly thought about while making a code change. So that gets missed out. So these abstractions on providing our internal developers, they create some issues, and we probably want to make it better by documentation or building few templates for them, and more demos internally for them to get started. Another situation we are talking about is monolith. As I was talking in my previous slide, when you are importing or in monolith, it's a very good situation for you to reuse code. But here, while we are defining workflows with temporal, if we are not cognizant of what we are importing or how our workflow looks like with reuse of code, we end up in a situation where we introduce unnecessary bugs and side effects while defining the temporal workflow. So we're working on simplifying by end-to-end tests, which we can catch these bugs before we throw them to production. Also, we probably want to define a code structure in which we can catch these at the build steps through static analysis of code. And we also want to build some patterns of common patterns. One of the common patterns is scatter-gather pattern. We want to build templates around or scaffolding around these so that it becomes much easier for a new developer to write their workflow code. So glancing into the future, we plan to build a custom dashboard for ourselves. We are planning to encrypt our inputs and outputs because since we are dealing with employee data, we might run into situations of handling PIIs. So we'll be building a custom dashboard which can add access controls around the workflows on who can access a particular workflow and who cannot. So we'll also work with native integrations with Datadog and Sentry for easy debugging. So that helps us minimize our operational cost. So we spoke about ETA at the start of this talk. We want to bring workflow as a native programming concept. So I think ETA is a good place where we can build these temporal abstractions internally. This can help us have a really good defined definition of a workflow. And it can help us with minimizing the configurations that are needed for a new team to onboard. And it is an abstraction building on the temporal SDK. Yep, that's all from us. Thank you.